Hi everyone, today we are going to talk about eigenvector and eigenvalue. So what is eigenvector? The eigenvector of a square matrix is defined as a non-vector in which when a given matrix is multiplied, it is equal to a scalar multiple of that vector. What is eigenvector equation? So let A be a non-matrix and the scalar lambda is called an eigenvalue of A of that is a non-zero vector x. And is so x equal to lambda times the matrix x, the vector x, and is formally known as the eigenvector equation. So the vector x is called eigenvector of A, corresponding to the eigenvalue of lambda. So there are two types of eigenvector, which are left eigenvector and also right eigenvector. So the left eigenvector is represented in the form of a row vector, and the right eigenvector is represented in the form of a column. So to find the eigenvectors of a matrix, we have to follow the procedure given below. First of all, we have to find the eigenvalues of the given matrix A using this equation, which is A minus lambda times I equal to 0, where I is equivalent order identity matrix as A. Next, we have to substitute the values into the equation Ax equal to lambda equal to this, or A minus lambda times I and then times x equal to 0. So normally we will use the second equation, which is easier for us to solve, and then we have to calculate the value of eigenvector x, which is associated with the eigenvalue. Lastly, we just repeat the step to find the eigenvector for the remaining eigenvalue. So now we look for an example to let us have a better understanding on this chapter. The question is determine the eigenvalues and eigenvector for the matrix B equal to 1, 2, 3, 2. So let us look at the solution. So the B will be 1, 2, 3, 2. The eigenvalues lambda of matrix B satisfy the characteristic equation. So as I mentioned before, we will use this equation to solve the question. So B, the matrix B minus the eigenvalues lambda multiplies by the identity matrix, which is 1, 0, and 0, 1 equal to 0. So we will times the lambda with the identity matrix first, and then we use the matrix B to minus the value, and then we will get this. Therefore, we will get lambda squared minus 3 lambda minus 4 by using the cross multiplication, and then by pressing the calculator, we will get lambda equal to -1 and 4. Hence, the eigenvalue of matrix B are -1 and 4. So, to find the eigenvector, we have to substitute the eigenvalue into our equation. So when lambda equals to -1, we have 1, 2, 3, 2 minus x1, x2 equals to -x1, x2, as I mentioned before the equation. Or another equation, which is 2, 2, 3, 3, x1, x2 equals to 0. So we will be using this equation to solve the question. Therefore, 2x1 plus 2x2 will be equals to 0, or x1 and then x2 will equal to -x1. So we assume that x1 will be equal to k, where k is a constant. So x2 will be equal to negative k, then x will equal to k. X is a eigenvector, so it will be k and negative k. Will be a raw vector, and then will equal to pull out the k, and the vector will become 1 and negative 1. So the corresponding eigenvector is 1, negative 1. So just repeat the step to find for the remaining eigenvector. So we substitute lambda, which is the eigenvalue, equal to 4. So we have this equation, minus 3, 2, and 3, negative 2, multiplied by the eigenvector equal to 0. So the negative 3 times x1 plus 2 times x2 will be equal to 0, and then we solve the x2. So x2 will be equal to 3 over 2 times x1. So we assume that if x1 is equal to 2k, where k is a constant, so x2 will be equal to 3k. And then our eigenvector s will equal to 2k and then 3k, and we pull out the k, so our eigenvector, so the corresponding eigenvectors is 2, 3. So that is a solution for finding the eigenvalue and also eigenvector. That's all from me. Thank you.
Initiator is vector space. Definition of vector space is a space comprised of vectors collectively with the associative and commutative law of addition of vectors, and also the associative and distributive process of multiplication of vector by scalar is called vector space. For the vector space, it can be separated into two types. The first one is the vector addition, and the second one is the scalar multiplication. The vector addition is the two vectors u and v indicates in the v, and it produces the third vector is the u plus v indicates in the v. The scalar multiplication is takes a scalar c indicates in f and a vector v indicates in v, and it will produce a new vector u multiplied with v indicates in v. The condition for to process is the element of v are mostly called vector and the elements of f are mostly scalar. They are different types of vectors. And here is all the properties of vector space. To prove u plus v equal to v plus u, we start with f plus g but multiply with t by using the definition of sum of function and the commutative law of addition for real number, and also the definition of sum function. We will get the g plus f multiplied plus t. So therefore, we will get u plus v equal to v plus u. Lastly, to prove a multiplied with u plus v equal to au plus av, we were using two definitions, which is definition of scalar multiplication and the definition of sum function. We can see that we multiply the t into the bracket f plus g, so you will get the ft plus gt multiplied with a. After that, we multiply the a into the each element, which is a equal to ft and plus a equal to gt. Lastly, we take the t outside, so we will get af plus sg. Therefore, we can prove that a multiplied bracket f plus g equal to af plus ag.
Subspaces. Definitions. A subset W of a vector space V is called a subset of V if W satisfies the following properties. The first one, a zero vector of V is in W, and whenever vector U and V belongs to W, then U plus V belongs to W. And whenever U belongs to W and alpha is scalar, then alpha U's belong to W. So let's look at the example of subspaces. And let W be the set of all n cross n matrix M with trace equals to 0, and show that W is a subspace of M. Since the n cross n matrix M has trace equals to 0, it belongs to W. And suppose that A and B are matrices in W, and therefore trace bracket A plus B equals to trace A plus trace B, and trace A and trace B equals to 0 respectively, and their total will be 0. And for any scalar alpha, trace bracket alpha A is equals to alpha trace A. And since trace A equals to 0, alpha multiplied 0 will also equals to 0. And therefore, A plus B and alpha A are in W. And hence, W is a subspace of M.
Hi, my name is Joanne Liu Xinghui, and now I'm going to talk about what is linear combination. So, in mathematics, a linear combination is an expression constructed from a set of terms by multiplying each term by a constant and adding the result. For example, a linear combination of x and y will be expressed in the form of y equal to ax plus by, where a and b are constant. Given vector v1, v2, v3 until vn, a linear combination of this vector has the form of v equal to c1 v1 plus c2 v2 plus c3 v3 until cn vn, where c1, c2, c3 are the scalar, while v1, v2, v3 are the vector. So in short, what is linear combinations? A linear combination of those vector is simply a sum of scalar times those vector. So in order to have a better understanding of what linear combination is, we will have to look at some example. So now let us see our example. Given vector x1, 1, 2, 3, and vector x2, 4, 5, 6. Find alpha and beta that gives the linear combinations of y, 14, 19, 24 in terms of vector x1 and vector x2. Before we solve the example, we have to bear in mind the equations of linear combinations, which is v equal to the sum of scalar times those vector. So with that in mind, we can easily solve the example. And now we are going to see the solution. So in this example, we are going to determine what is alpha and beta. By using the equations, y equal to alpha times vector x1 plus beta times vector x2, and substituting vector x1, vector x2, and linear combinations, which is y, into the equation, we are going to obtain two simultaneous equations, and by solving the simultaneous equation, it gives us alpha equal to 2 and beta equal to 3. Therefore, the linear combinations of 14, 19, 24 is equal to scalar 2 times vector x1, which is 1, 2, 3, plus beta, which is scalar 3 times vector x2, which is 4, 5, 6. And in other words, the linear combinations of 14, 19, 24 is one of the many possible linear combinations of vector x1 and vector x2. And so now we are going to proceed to our next subtopic, which is speed.
Alright, I am Kojajin, and I am going to talk about span as a subtopic for eigenvalue and eigenvectors. In the mathematical subfield of linear algebra, the linear span, also called as the linear half of a set of a vector in a vector space, in the intersection of all subspace containing the set, the linear span of a set of a vector is therefore a vector space. So, what is span? Span is the span of a non-empty subset S of a vector space V. Is a set of all the linear combinations of vector in S. This set is denoted by span S. If S is equals to V1, V2, V3 until Vn, subset to V, then span S is equals to span V1, V2, V3 until Vn. So, let's talk about an example. In the vector space, write M as a linear combination of all the matrices in S which is containing A and B. It is given that M is equals to 2, 1, 1, 0, A is equals to 1, negative 4, 5, 3, and B is equals to 1, negative 1, 2, 1. we have to show that M is a subset of the span S. Firstly, we have to let alpha, beta, gamma to be constant such that M is equals to alpha A plus beta B. Then we will get the third row equation, which is 2110 equals to alpha times with 1 negative 4 5 3 plus beta times with 1 negative 1 2 1. Hence, we obtain simultaneous equation with two unknowns, which is alpha plus beta equals to 2, negative 4 alpha minus beta equals to 1, 5 alpha plus 2 beta equals to 1, and 3 alpha plus b equals to 0. Then we are solving this simultaneous equation give us a unique solution, which is alpha equals to negative 1 and beta will equals to 3. Then we sub the alpha value and beta value into the equation. We will get that 2110 equals to negative 1 times with 1 negative 453 plus 3 times with 1 negative 1 2 1. So the above expression show that the M is equals to negative 1a plus 3b. It's a linear combination of all the matrices in set S. Therefore, M is a subset for the span in containing A and B, or we'll say that M is a subset for span S. So, the importance of a span in our real life is a span is a pretty simple object in a linear algebra when we're solving a mathematical questions. It's simply the collection of all the linear combination of the vectors. Normally, its use is in everything from machine learning to organic chemistry. So that's all for my part. I will let Hui Xin to explain the next part. Thank you.
Next, we are going to talk about linearly independent. A set of vectors is linearly independent if the summation of constant times vectors from 1 until n is equal to 0 and all the constant values are equal to 0. If not all the constant values are zeros, we can say that the vectors is linearly dependent. In linear algebra, a family of vectors is linearly independent if none of them can be written as a linear combination. A family of vectors which is not linearly independent is called linearly dependent. For example, we have four vectors here, P, Q, R, and T. P is 0, 0, 1, Q is 0, 2, negative 2, R is 1, negative 2, 1, and T is 4, 2, 3. Vectors P, Q, and R are linearly independent. However, vectors T is linearly dependent because it can be written as T equals to 9P plus 5Q plus 4R. These four vectors together are linearly dependent. Let us see an example. The question asks us to test the following polynomials for linear independence. For those sets that are linearly dependent, express one of the polynomial as a linear combination of the others. We have the vectors x minus 1, 5x squared plus 2x minus 4, 15x squared plus 14x minus 20. We let alpha and beta be the constant such that 15x squared plus 14x minus 20 equals to alpha times x minus 1 plus beta times 5x squared plus 2x minus 4 equals to 5 beta x squared plus alpha plus 2 beta times x minus alpha plus 4 beta. Hence, by comparing the coefficient of x squared, x, and the constant, we can get that 5 beta equals to 15, alpha plus 2 beta equals to 14, negative alpha plus 4 beta equals to negative 20. By solving this simultaneous equation, we can get that alpha equals to 8 and beta equals to 3. Since alpha equals to 8 and beta equals to 3 and both are non-zero, we can conclude that the set of polynomials are linearly dependent. Thus, 15x squared plus 14x minus 20 equals to 8 times x minus 1 plus 3 times 5x squared plus 2x minus 4.
This is our reference, and thank you.